California, home to 40 million people, and the sprawling megacities of Los Angeles and San Francisco. In the last century, the most populated state in the US has grown 50-fold. Yet the region faces a terrible threat: the earthquake of the century.
We call it the big one because we expect the next San Andreas earthquake to be in the upper magnitude 7s to a magnitude 8, which is a very large earthquake.
Magnitude 8 in a highly populated area can cause a huge amount of damage.
But how much is it going to cost? How many lives are going to be lost when we have another big earthquake? It's going to be tens of billions of dollars and hundreds, if not thousands, of lives lost.
To blame, a gigantic crack in the Earth's crust spanning more than 1,200 kilometers between the two megacities.
Here, we're in the San Andreas Fault area, in one of the very few places where you can actually see and touch it. Literally, on either side of this fault, you have different tectonic plates.
Anytime you can sort of go up on a hike and be high looking over the big city down below, you're standing on top of an active fault.
For over 40 years, the fault has been ominously quiet. Everyone knows that the big one is coming. Even overdue. So when will it happen? What will it look like? How can we prepare? Is it even possible to predict it? To answer these questions, scientists study the geological history of the fault.
So we date the different layers, and then we can determine when earthquakes occurred in the past.
Every meter of the fault is mapped out, every movement scrutinized. Scientists have developed an ultra-sophisticated warning system.
With seismometers, we have approximately 1,400 of them spread across the West Coast.
Every time we can gain a few seconds, we can save lives, and that's important.
When the big one strikes, what shape will it take? You're about to see the two most likely scenarios envisioned by scientists. One in the San Francisco Bay Area.
What you're supposed to do is drop cover, hold on, get under a table, get under something sturdy, and wait.
And the other in Los Angeles.
It's quite spectacular to see how the seismic waves can liquefy the ground. Entire apartment blocks can sink several feet into the ground.
So if you think of some Jell-O and you hit it on the side with a knife or a spoon and the Jell-O jiggles, imagine downtown Los Angeles shaking out that bowl of Jell-O.
These earth-shaking scenarios foretell catastrophic consequences. Hundreds of lives lost, thousands injured and homeless. The big one is coming. There is no doubt and no stopping it. Is California ready? October 17th, 1989. A peaceful late afternoon in San Francisco. Most people are at home so as not to miss the start of the Baseball World Series final. Two Californian teams are vying for the title, San Francisco and Oakland.
At home for the Giants, one of the most spectacular vistas on this continent, any continent. Downtown San Francisco in the background, and we zoom into Candlestick Park.
Jason, too, is in front of a screen, waiting for the game to start.
So I was sitting there watching the World Series, very excited. The game hadn't started yet, and then poof, everything goes off the air. I'm like, what is going on here? What's wrong?
And he fails to get Dave.
5:04 p.m. The broadcast is suddenly interrupted.
Take. I'll tell you what, we're having an earthquake.
A 6.9 magnitude earthquake shakes the entire region. More than 15 seconds of panic.
What happened? There's a hell of an earthquake.
I remember the noise very much. It was so loud. And then all the large windows started to fall out onto the sidewalk. It was moving a lot. I remember grabbing the table in front of me, and I thought, oh no, this is it. I don't know what that means, if this is the big one or if this is the end, I don't know.
How is it the emergency?
Cypress section of the West Grand Freeway has come down.
The Cypress structure has collapsed. 25238, we have a major injury accident.
And I walked out onto the street, as did a lot of other people, and it was like looking over a war zone.
Our Cypress structure in Oakland has just fallen through. The structural collapse of the entire freeway.
There were fires. The marina right over there was pretty much all on fire. There was a huge fire, a big, huge flame. And around the city, there were pockets of flames.
The earthquake started in an area called Loma Prieta, more than 100 kilometers away from San Francisco. The seismic waves spread through the entire area in less than a minute before reaching the San Francisco Bay Area. San Francisco is on fire. 63 lives are lost and more than 3,000 people are injured. A few years later, barely back on its feet, California is shaken again by a 6.7 magnitude earthquake.
For 15 million people in Los Angeles, this was yet another 30 seconds of terror.
A few years after that, another earthquake hits, this time in Napa Valley, Northern California. Since the start of the 20th century, hundreds of earthquakes, both minor and major, have been occurring along a line that crosses California from south to north, cutting the state in half. This line is known as the San Andreas Fault.
If you are flying, anytime you fly from Los Angeles to San Francisco, you're going up the San Andreas almost the whole time. So if you sit on the correct side of the plane, you can just watch it. Mostly if you want to look west, usually outside of the plane.
It is about 1,200 kilometers long, and so in places you'll see a little hill created that will actually show where the fault is located, and that could be through showing potentially ripples, and that is where it shows. And so pictures that you see in textbooks show that sort of rippled landscape.
The path followed by the fault endangers more than 2/3 of California's population. That is almost 30 million people.
Along the San Andreas Fault, there are several major cities. Obviously, in the south, you have San Diego and Los Angeles. Los Angeles represents more than 10 million people, and further north, you have San Francisco. And so, it triggers extremely powerful earthquakes with magnitudes of over 7 or 8 in very populated areas.
I've been in many big earthquakes in my life, and we live in earthquake country, so we're always thinking about these things. Earthquakes are going to happen. It's not a matter of if, it's just a matter of when they're going to happen.
California is one of the most seismic areas in the world, but also one of the most populated. When will the big one happen? And how strong will it be? These questions have been asked since the early 20th century, when an unexplained giant earthquake destroyed California's largest city, San Francisco. 1906. The city is booming, its streets teeming with people and incessant activity. But a few hours later, everything will change. 5:10 p.m. The earth starts to shake. More than 40 seconds of terror for the city's sleeping residents. At 7 a.m., San Francisco is in total chaos. Uncontrollable fires rage for 2 days. Water is scarce, and people flee in panic. The entire country is traumatized. How can a city this size have been destroyed in just a few seconds? The scientific community wants to understand what caused the earthquake, and especially whether it can happen again.
The earthquake occurred about 50 years after California became a state in 1850, and it affected the most industrialized, largest city on the West Coast, San Francisco. And so it really sort of figures in history as impacting a really important place and where a lot of people were affected.
And because it was felt over such a big area and had such a huge impact on San Francisco, the scientists went out to study that, to understand how long is this fault, how far does it extend.
A team of scientists is rapidly put together, led by Andrew Lawson, a researcher at the University of Berkeley.
It's the first time that scientists go out into the field with their little notebooks, etc., and they start mapping the fault. So that's a major shift. And that happened because it was California. Earthquakes have always happened, but when they happen deep in the steppe, in Asia, in the 20th century, there's no one to talk about it.
It was more than taking pictures. It was really assembling a team of scientists and very carefully document everything about the earthquake. So yes, people went out and walked along the fault line and mapped the earthquake rupture in great detail and took a lot of pictures.
By roaming the area and analyzing photos, the team of researchers quickly realizes that this earthquake is unlike any other.
So with all the mapping that they did, Andrew Lawson and colleagues, they were able to see that along the fault there were displacements of as much as 7 meters, right?
And what really surprised him was this fault moved sideways, totally different than all the faulting that he had thought before, or he always thought faults occur up and down, but this one occurred sideways.
That's actually the first time that we realized the Earth was being deformed. That's when it clicked.
The San Francisco earthquake shifted the Earth from north to south. Huge areas of land literally slid past each other.
And what does he see? Mainly fences, roads, sometimes even natural objects like a riverbed that were shifted by the fault. He knew that far away from the fault line, things were moving. So he developed this so-called elastic rebound theory, where the Earth deforms far from the fault, but the fault is locked because of friction until crack. There's this elastic rebound.
It's like stretching an elastic before it snaps. You can stretch it for a long time before it snaps. And so the fault works in almost the same way. It can deform over many years, and at one point, which we would all like to predict, it will rupture in an almost immediate earthquake.
But why does the Earth's crust move? At the time, nobody knows. Scientists decide to index every earthquake around the world. Their aim? To see whether their location can give any clues on their mechanisms. They discover something surprising. Earthquakes are triggered along very precise lines. These imaginary lines mark out large plates more than 15 kilometers deep, also known as tectonic plates. These plates move very slowly in relation to each other.
A century ago, we didn't know about plate tectonics. We didn't know about plate boundaries. And so we've made a great deal of progress since we now know that more than 90 or 95% of destructive earthquakes occur along plate boundaries.
You have these rigid plates moving whichever way they can, and all of these plate boundaries are formed by faults. So you have subduction faults, you have extension faults, and you have places where the plates slide along each other, essentially horizontally, like the San Andreas Fault.
The San Andreas Fault concentrates the continuous movement of 2 huge plates over 1,200 kilometers.
The San Andreas Fault is actually the boundary between the Pacific Plate on the west and the North American Plate on the east. And what's happening is that the western part is moving north. So if you look at your thumbnail and you imagine that it grows about 50 millimeters per year. So imagine your thumbnail growing, and that's how fast Los Angeles is getting closer to San Francisco every year by about 50 millimeters.
The main driver is that the whole time the tectonic plates are always moving. They're locked at the faults, but then far away from the faults, they're always moving. So you're always accumulating that energy that you need to release in an earthquake.
You accumulate tectonic forces, as they're called, and then you reach breaking point, and that breaking point is an earthquake. And this earthquake will level out the two sides of the fault. Then a new seismic cycle will start, with a new accumulation of tectonic forces that will lead to new earthquakes.
Scientists understand that the fault is locked in California, while the huge tectonic plates continue to move in the middle of the Atlantic Ocean to the east, and all the way to Russia in the west.
We can measure the speed at which these faults move, so we know the slip deficit that is accumulated along these faults. And we have already exceeded the amount of slip released in previous major earthquakes, so basically, it's ready to happen again.
And so the concern is that there's going to be an earthquake, a big one as we refer to, which is the high magnitude 7 earthquakes, like magnitude 7.8, which is sort of the typical large earthquake on the San Andreas.
An earthquake of this magnitude could, according to experts, cause hundreds of people to die, thousands to be injured or homeless, and millions of dollars of damage. The stakes are colossal. This is why scientists have only one thing in mind: being able to predict when exactly the big one will happen.
The when depends on the timescale you consider. If you're talking centuries, yes, we can predict it. We know there will be a very large earthquake in the coming century, but that's not what interests us from a societal point of view. I always talk about the timescale of insurance companies who want us to predict earthquakes within a 3-day window. Otherwise, if you move a population like that of Los Angeles for more than 3 days, the financial cost is so high that it isn't profitable, and they're better off compensating people for the damage. It's a bit of a cynical calculation, but that's how you've got to think.
In order to predict the next earthquake, we need to know the fault's movements down to the very last detail. Scientists have thoroughly mapped out its 1,200 kilometers and obtained a precise plot of the path it takes. It starts on the shores of the Salton Sea in Southern California. It then heads up north, skirting Los Angeles, before continuing through the valleys around Pasadena.
We are standing on top of 2 tectonic plates at the boundary of these plates. On this side is the Pacific plate, then on this side is the North American plate. And so if there's an earthquake here, interesting thing will happen. To my right, there is a university. And if we were here during the earthquake, this university would move in a few seconds 10 meters that direction. That's a pretty big distance.
It then curves and forms steep mountains. It fractures the Earth's crust in the Carrizo Plain, lifting the ground and compressing it.
We're very close to the San Andreas Fault, and you can see here a perfect example of how the Earth deforms because of the colossal pressure and forces at play around fault lines.
It makes its way in a straight line to San Francisco, which it cuts in half before finally flowing into the sea, a few dozen kilometers further. By analyzing the fault, scientists discovered that it doesn't move the same way everywhere.
So the San Andreas Fault is interesting because it does have 3 sections. The southernmost and the northernmost are always locked until they're having an earthquake, and then they release all of that tectonic strain that's been developing. The middle section is sort of unique for much of California, at least, in that it sort of keeps up with the tectonic rate of the plates.
Which means it's constantly moving a little bit every year. And so because of that, it doesn't build up elastic strain energy. It doesn't build up, the rocks don't bend and build up that elasticity to the point where they break and snap back into shape.
The south of the fault in San Francisco and the north in Los Angeles are therefore the most seismic areas. But the rest of California is no better protected. as what scientists discover is not reassuring.
The San Andreas isn't really just a single fault, it's a system of faults. And in fact, we're out on one of the branches in Southern California called the Elson Fault. And the San Andreas is really the biggest player, but it's by no means the only fault that could produce significant damage.
So here in the San Francisco Bay Area, we have at least 4 other faults that are named and are considered capable of producing their own great earthquakes. So that's namely the Hayward Fault that goes right here through the university campus, the Calaveras Fault across the East Bay Hills, and several other faults.
The fault seems to be everywhere. There's a piece of the main San Andreas, maybe, a quarter mile to the right. There's more pieces of it, splays of it back here to the left. That's a composite of a whole bunch of different segments of faults that are roughly parallel, running very near each other and connecting with each other.
A map gradually emerges. California is crossed by a multitude of faults, with the most important at its center, San Andreas.
What actually is an earthquake? It's a fracture that spreads. But if I start looking at the point where it breaks, there are all sorts of little cracks before it gives way completely. The Earth's crust is the same. If you look closely at a fault, you'll see a branch here and here and here.
So we really live on a very active plate margin, which is also very broad. So it's distributed out over tens to hundreds of kilometers. In fact, there's faults that go all the way to the east.
The San Andreas Fault and its multiple ramifications worry seismologists. How can they precisely predict the time and location of the next earthquakes? To answer this, researchers have decided to index past earthquakes and see whether any cycle is repeated.
This is the main fault for the Elsinore Fault, and it separates Pliocene sandstone from these Quaternary alluvial fan deposits, which are about 40,000 years old. And these have been translated about 60 to 70 meters to the northwest relative to the sandstone. So this is the primary slip surface right there. Most of the slip will occur right along that fracture, and there are stria on this that are horizontal. So you can tell the motion, the direction of motion on this fault is virtually pure strike slip. But this is what we call the principal slip surface. That's beautiful.
By digging trenches perpendicular to the fault, scientists can go back in time.
So we excavate trenches across the fault, and we study the interaction between fault motion and sedimentation. So we like to find sites where you're having deposits of silt and sand and clay periodically put across the fault. And so the game is to identify where was the ground surface during a large earthquake. So we date the different layers, and then we can determine when earthquakes occurred in the past.
It helps determine or date past earthquakes, and that gives us an idea of what we can expect in the future. If we know the recurrence times of a given fault, we can reasonably believe they'll be similar going forward.
Each earthquake fractures the Earth's crust. Then, as the years pass, a layer of sediment is deposited until the next earthquake, which again fractures the ground, which again is covered in sediment, and so forth. It is therefore possible to go back in time over millennia and determine the dates and magnitudes of major past earthquakes.
So if you look at all the studies that we've done along the San Andreas Fault system in California, Northern and Southern California, we can develop a chronology, tell how often they occur, and some degree of variability.
Technically, we see that the average is 100 to 150 years, depending on where you are. And it's been 100 to 300 years since we've had a major earthquake.
So, you know, when we say the fault is now beyond its average recurrence time, you know, that's a concern. That's why we say we're waiting for the big one.
But what worries researchers the most are the earthquake cycles.
If you start looking in detail, you notice that there are what we call earthquake storms. It's more of an image, but there are moments when it's best not to be in a certain area, because the entire fault ruptures and ruptures several times, and then there are moments of calm.
This is the case of the San Francisco Bay Area. Before 1906, there were more than 11 major earthquakes in 75 years, against only one since.
So 8 million people or so moved to the Bay Area in a time that was unusually quiet when it comes to the occurrence of earthquakes. So now we might be getting back to a more normal frequency of earthquakes, and that would suggest there should be a magnitude 6 or bigger earthquake every decade or so, every 2 decades, rather than having had many decades of almost none of them.
You know, if you have a rupture and then just 10 years later, when you're finally sort of coming back together and you've done all this rebuilding and you have another earthquake on the next section, then you're back at square one. And so there's a different kind of challenge rather than the sort of immediacy of one big earthquake, is having them in close enough succession that societally, economically, culturally, you're just getting over one earthquake when the next one happens. And that's kind of a different.
How do they start? Are there any warning signs? Scientists decide to study an earthquake in real time. But first, they need to know where the next one will happen. The solution may lie in Parkfield.
Parkfield is a small town. Not many people live there, but it's located bang on the San Andreas Fault, in a place that generates magnitude 6 earthquakes every 20 years or so, with a factor 2. And so it gives the opportunity to each generation of scientists to test the latest ideas, the latest models, and to check whether or not we can predict earthquakes.
In 1922, 1934, and 1966, the earthquakes at Parkfield all started under Middle Mountain. And we have seismograms for them, so we know where they started, and the seismograms are identical, virtually identical.
Parkfield earthquakes occur regularly. The next one is expected in the late 1990s.
One of the difficulties when it comes to earthquakes is actually the duration of observation. Human life is a little too short to be able to observe several major earthquakes on the same fault line and to check how regularly they happen, which is what we call recurrence. We don't live long enough. But Parkfield had this particularity of generating earthquakes that weren't necessarily of the greatest magnitude, but that were extremely regular.
And so scientists said, oh, these earthquakes happen so regularly, there's going to be a big earthquake in 1988, which is 22 years after the last one in 1966. It's going to be a magnitude 6 again, and we should put out all the instrumentation possible. And if we do that, we're going to catch something that will allow us to understand how to predict earthquakes.
From 1989, scientists set up a drilling station to penetrate the Earth's crust as deep as possible and collect rock samples from close to the fault.
What's really great about this experiment is that they were actually able to dig deeper into the Earth by over a mile to find out what's happening down there, to get a sense of what does the fault look like at depth, and to understand what does the rock look like, what's the composition of the rock, how is it hot, is it cold, what's happening. So that particular study gave us a glimpse into what's actually happening deep inside the Earth, which is we don't get that very often.
They drilled down to approximately 3 kilometers under the Earth's surface, collecting rocks in several places in order to analyze them. Could these rocks change after an earthquake and provide us with more information? We'll need to wait and see.
So they put all sorts of instruments around Parkfield, and they held their fingers in their ears waiting for it to go off.
Except disaster. The last predicted earthquake didn't happen, or at least it didn't happen in the predicted time frame.
It happened in 2004, and it didn't start like the others. It started 20 kilometers further south. So it did the opposite of every previous earthquake.
Nothing happened in the days, hours, weeks before the earthquake that anybody could claim could have allowed us to predict the earthquake. So that was a big reality check.
Nothing happened as expected.
It turns out that experiment, the Parkfield experiment as it was referring to, didn't end up being an earthquake prediction opportunity. We were expecting to be able to say that earthquakes happen over these time periods, repeat over certain periods of time. And the interval was something in the order of every 20 or so years, and it didn't work out for us.
So we realized that this accumulation of 4 or 5 earthquakes that had been kind enough to happen at regular intervals was more of a coincidence, or that there may have been a physical reason we didn't understand, but it certainly wasn't a set rule.
But all is not lost. Scientists analyze the hard rocks around the fault. They have literally been crushed and subjected to very high temperatures. Where does this heat come from?
Earthquakes are frictional contacts between solids, so they generate heat. It's the same principle as warming up your hands by rubbing them together when you're cold. Temperatures can change by several hundred degrees for a few seconds. And there are questions as to whether these temperature rises could explain the propagation of earthquakes or their nature. And so, to try and predict earthquakes, we need to understand the role of temperature.
The friction of the plates generates heat. The rocks are damaged and crumble. The plates slide. The movement accelerates. The heat increases. The cycle climaxes and ends in an earthquake. Could temperature be the first sign of an earthquake?
The material analysis, by looking at the amount of heat that's built up along the fault, the amount of heat that's stored, the amount of liquidity that's down at depth along this fault, is going to be an important piece of information that comes from it. And that goes a long ways to understanding what stresses have to build up before an earthquake flattens San Francisco again, or Los Angeles.
For now, everything is up in the air. Parkfield seems to have been abandoned while we wait for the next earthquake. The instruments are in place, and other avenues are being considered.
Some people think that electromagnetic signals are emitted before an earthquake. There are also chemical signals, such as the emission of certain gases like radon. Temperature is one example among many, but honestly, I'm not sure it's very reliable yet.
My sense is that will improve our understanding of the earthquake system. It will be relatively unlikely to allow us to actually predict earthquake with any confidence.
So what we want is something that we say that can happen over certain defined periods of time. And if you start applying exceptions and start saying, well, under these conditions it does this, under those conditions it does that, then it ceases to be a really good model to predict earthquakes.
The San Andreas Fault is ready to shake. Scientists have known this since 1906, but have so far been unable to give a precise date or detect any early warning signs.
By its nature, earthquakes are chaotic, meaning even the littlest change in the system, right? The butterfly effect, even just a little kink in a fault or a certain aspect of an earthquake when it happens changes the system enough that it's never going to be predictable, that no matter how sophisticated a simulation you build, it will never truly allow you to predict what's going to come next.
To be clear, today, we don't know how to predict when earthquakes will happen. We test, we have a lot of ideas, but we're not yet capable of making quantitative predictions.
In terms of prediction, we're a little stuck.
I'd say when I got into this business 40 years ago, there were a lot of people that thought we were on just on the cusp of predicting earthquakes. I'd say now we know we're farther away from that point than we thought we were 40 years ago.
Seismologists have reached an impasse, and California's population continues to increase, as does its construction, creating more and more megacities. It is vital to be able to warn residents. So, scientists have come up with a solution.
We have access to a lot of data. We know the seismic history of many faults around these cities, and so we're able to make certain statistical risk predictions. Some models are sophisticated enough to be able to assign a probability of occurrence of a certain magnitude earthquake over a certain time period.
And so we choose, say, 30 years because it's a time that we can all deal with. Human generations are like 30 years. Home mortgage is 30 years.
We can write a probability distribution that in the next 30 years, it has a 10% chance of rupturing. In the next 50 years, it might be 20%. In the next 300 years, it might be 80%.
So they all come down into those final numbers, and there's many different models that are used, and you sort of weight them based on how confident you are about that model or that submodel.
What's going to happen in the next 30 years around the San Andreas Fault? Which city is most likely to experience the big one? San Francisco? Los Angeles? Santa Cruz? The population must be made aware of the incurred dangers living in California. In the San Francisco Bay Area, there is a 70% chance of the earthquake of the century happening in the next 30 years. Seismologists have even detailed the probability on every active fault, each one threatening a major city.
That allows us to say, well, in the next 30 years, the probability of an earthquake on the Hayward Fault is about 31%. We know it had one in 1868, that was a magnitude 7, and it's right stretching along the most populated area really in all of California. So it's a major player.
But there is also the Rogers Creek Fault near Santa Rosa, with a population of 170,000, or the San Gregorio Fault that runs along Santa Cruz with a 10% risk.
If you just say, oh yeah, it's likely, it's got a 10% chance in the next 30 years, that means maybe a 90% chance that it won't rupture. So, a lot of people will think, I'm not going to worry about it. But you should worry about it. Because some of these faults now are well beyond their average recurrence times. And the probabilities are really quite high from a geologic perspective for the San Andreas in particular. So that is the one we really worry about. And when it does rupture in a large earthquake, it will be a big one.
Further south, around Los Angeles, there is a 75% risk of a giant earthquake of magnitude 7 or more.
And that's a magnitude 7.8 earthquake, which occurred along a 300-kilometer long segment of the fault. That earthquake would affect almost all of Southern California and cause all kinds of disruptions from, people being injured to critical infrastructure being affected and that kind of thing.
Ultimately, there's a greater than 99% chance of a big one happening somewhere in California in the next 30 years.
But a forecast has a really important societal value because they're 30-year forecasts, and that helps you decide what infrastructure you're going to repair first.
We need to protect our infrastructure, our hospitals, our schools, and so we need to make informed decisions.
So I was just talking to a city today that was describing how they haven't updated any of their fire stations in decades. And so you might say, well, if we have high odds of an earthquake here, we should probably have fire stations that can withstand the earthquake and then be able to help people after it.
These figures are a terrible reminder of the threat to Californians.
Really is one thing understanding that you live in earthquake country and that things are going to happen, earthquakes are going to happen. but it's having a emergency supplies kit, like with water and with food and medical, your prescriptions, and having some money because ATMs are not going to work after an earthquake.
Yeah, we should always be prepared for an earthquake in California.
It's going to happen, for sure. And because it's going to happen, the idea is that we have to be prepared. The population needs to be educated. And we need to try and reduce the impact of the earthquake on infrastructure and the number of victims.
Preparing for the worst. Scientists are not throwing in the towel and will deploy all the technology at their disposal to protect residents as best they can. To do so, they will start by deploying one of the most sophisticated earthquake warning systems in the world.
The idea is that if you could detect an earthquake quickly enough, meaning once that earthquake reaches the surface of the earth, which sometimes then you take that information and you move it to a place where you can figure out like where is the earthquake located and how much is it going to shake.
The idea is therefore to capture seismic waves triggered by the earthquake using ultra-sensitive seismographs.
When the rupture spreads, it emits different types of waves. First, it emits so-called compressional waves, like sound waves, that travel very fast. These are also known as P waves.
They're traveling ridiculously fast, 5 miles a second, and they hit. And then a couple seconds later, the S waves, which are totally different. Instead of being compression waves, they're shear waves, and they're going to hit you.
And that's much stronger, and it moves a little bit more slowly. And so if we feel the shaking from that P wave, that actually gives you also a little bit of time to maybe protect yourself, because the much stronger shaking is still to come.
First, the P waves reach the surface of the Earth and spread extremely rapidly. A few seconds later, the S waves emerge, moving in such a way that they spread less fast than the first waves. It's this delay between the two wave trains that will allow scientists to develop a warning system.
The first compressional wave is the one the sensors will detect immediately. Even you, if you're in bed, you'll feel something. And if you're a seismologist, that's when you start counting. Because you know the propagation speed of the waves. And you wait to feel the second tremor before saying, okay, that's X many seconds, so X speed, so X distance. In the context of the big one, I think you'll be shaken pretty hard by the first wave, and you'll have better things to do than start counting.
Seismologists will capture the first waves, the P waves, in order to sound the alarm before the more devastating second wave train hits the city.
Think of earthquake early warning like a race, and we're trying to outrun the seismic waves. We're trying to get information out ahead of those waves that are moving through the earth.
This race against seismic waves comes down to the second. In order to win it, scientists have deployed more than 1,500 seismometers along the San Andreas Fault and the secondary faults. But that's not all.
That information is moved to the processing center. So essentially the brains of the operation are these processing centers. In fact, here in Pasadena, this is one of the processing centers right here where we're located. And it all happens in a matter of just a few seconds. And that's the important thing is that this is one of the key innovations. We've been using seismometers for years, but the ability to process that information super fast is the real innovation here.
Just a month ago, I got a warning on my watch, and it was a magnitude 5 earthquake just south of here. But I got the warning before the earthquake happened, and I was in a meeting, and we dropped, covered, and held on, and it worked. So when a much larger earthquake will happen, and it will happen, it's probably going to make a big difference.
It's the airbag analogy, right? You can't predict an accident 3 days ahead, but when it does happen, you're glad you have an airbag.
A warning, even just a few seconds before the waves hit, can save lives.
There have been some earthquakes recently where we've collected a lot of data from closed circuit televisions. And we've understood like what people do when they feel shaking. And one of the major responses is people just freeze. They don't do anything. And so what we want people to do is not to freeze, but we want them to actually take that protective action, to do something about it, to protect themselves.
Preparing the population, anticipating, knowing what to expect. These are the challenges facing scientists. How fast will the waves spread? How long will residents have to protect themselves? Will the buildings hold up? To answer these questions, seismologists have simulated the most probable Big One scenarios in California's two most at-risk megacities. Up north, the Hayward Fault represents the greatest danger. Several million people live and work nearby. Major earthquakes occur every 150 to 220 years, and the last one dates back to 1868. At 0 seconds, the fault ruptures in the extreme southern part of the bay. The warning systems detect the first waves.
So the earthquake starts in the earth, reaches the surface in about 1 second. Information is moved from the sensor to the processing center in about 1 second. And then the processing center works on it, say, for about 3 seconds. And then it makes that information available to other people who then deliver alerts. That could take an additional 3 seconds.
7 seconds after the earthquake is detected, the warning goes out. But the earthquake has already wrought havoc at its epicenter, Fremont, a city of 220,000 people.
If you're close to the epicenter, there is what we call a blind zone, where the warning system isn't much use because the P waves and the S waves hit almost simultaneously.
One of the major factors is how far they're away from the epicenter. So distance matters. The idea is if you're farther away, then you'll have a little bit more time.
The P waves spread towards Oakland and Richmond. 5 seconds later, the more devastating S waves hit and caused the buildings to shake for more than 30 seconds.
The idea of the early warning system is to set a certain number of criteria based on the sensors in order to say something is happening that is abnormally strong. So we'll activate a certain number of security processes without even thinking. Typically, we'll shut down high-voltage electricity lines because we know that the wave train is coming, and we'll shake everything up, causing live wires to touch and cause a short circuit. We'll shut down gas supply. You can go through every red light. Everyone stops.
There are automated systems that shut down industrial manufacturing or open up fire station doors. There, even a second might make a big difference.
San Francisco is hit 26 seconds later, but the worst is yet to come.
It's often the secondary effects of earthquakes that cause the most victims. There are issues of water supply, issues of epidemics. There's a whole sequence of catastrophes that can happen. For example, very often, major earthquakes cause absolutely huge fires.
Fires are what destroyed San Francisco in 1906. To prepare for 400 potential fires starting, the city of San Francisco has buried more than 100 water tanks, marked on the ground, to which firefighters will be able to connect. In this scenario, scientists estimate that hundreds of people could die, more than 10,000 people could be injured, and 150,000 people could lose their homes. Another scenario, worse but also the most likely. Starting at the south end of the fault, its consequences are catastrophic. The earthquake is triggered around the Salton Sea. It is immediately detected by the warning system. The stopwatch starts.
So we did a scenario of the fault breaking all the way from the Salton Sea, all the way up to the northwest part of Los Angeles County. It's called a shakeout scenario, and it takes about 90 seconds for that rupture to move 300 kilometers. That's pretty fast.
Los Angeles marks the halfway point. The first waves hit at 35 seconds. But what will play against the city is its relief.
Los Angeles is built in a basin. It's essentially a big bowl. If you send waves in there, the waves hit, but that's not all. Unfortunately, they're reflected everywhere.
We're going to have waves spreading in the Los Angeles basin for several minutes, when they've already been and gone everywhere else. And so that creates waves that are bigger and last longer. Long enough, unfortunately, to bring down buildings.
And what happens with seismic waves when they hit these basins is they slow down and they get bigger. That means that things shake a lot more. So if you think of some jello and you hit it on the side with a knife or a spoon and the jello jiggles, imagine downtown Los Angeles shaking on that bowl of jello.
The waves bounce around the basin, creating another much more devastating phenomenon.
If you have a basin, you have a basin filled with sediment. And that means that you aren't on solid ground. You're on soil, on loose sediment. And that doesn't particularly enjoy being shaken.
When you shake the ground becomes liquid. It's kind of like when you're at the beach and you shake a stick in the sand. The water comes up and the ground softens. The same thing happens in sediment basins. It's quite spectacular to see how the seismic waves can liquefy the ground.
And that's a problem, because even if you constructed your building extremely well, if it ends up like this, it might not crumble, but it will fall down.
The city will be shaken for several long minutes before the earth calms down again. Is California ready for these earthquakes of unprecedented intensity in its ultra-industrialized cities? Everything is set up to warn the population, save lives, and protect infrastructure. Efforts and research are ongoing in this race against time. And the predicted big one.